This presentation is Module 2B of Chem for Bio at Northern Virginia Community College, Annandale campus. In this module, we will finish our discussion of elements and subatomic particles. Specifically, we will look at the biological importance of isotopes and then briefly cover the arrangement and the configuration of electrons in the atom. In Module 2A, we defined an isotope as an atom of a given element that must contain the same number of protons but has differing numbers of neutrons. In other words, two isotopes of carbon, carbon 12 and carbon 14. In carbon 12, there are 6 neutrons and 6 protons, but in carbon 14, there are 8 neutrons and 6 protons. They are both still carbon because they have the same atomic number, but they have differing numbers of neutrons, which gives them differing atomic masses and different physical properties. The average atomic mass of carbon is a weighted average of all the naturally occurring isotopes. I keep referring to stable isotopes and not stable isotopes, and that is because not all isotopes of a given element are stable. There are radioactive isotopes or radioisotopes. They are nuclearly unstable and they spontaneously emit nuclear particles and energy as they decompose into an element that is more stable. For example, carbon 14, although naturally occurring, it is radioactive and it slowly decomposes to nitrogen 14. What's the importance of isotopes in biology? Well, there are two biologically important uses of radioisotopes. The first is in dating fossil materials. An unstable isotope decays into a stable isotope of another element at a fixed rate. This fixed rate is called the half-life. And the half-life of any radioisotope is the time it takes for half of the sample to decay or decompose from the original isotope, called the parent, into a stable isotope of another element, the daughter isotope. Now, half-lives of radioisotopes vary considerably. Some radioisotopes have half-lives on the order of 10 to the minus 14th seconds. Other isotopes of other elements have half-lives of billions and billions of years. But the importance is that the age of an object can be calculated by finding the number of half-lives for a given radioisotope that have elapsed. Again, our best example of that is carbon 14 dating. If an object is organic, is biological in nature, and contains carbon, we can use carbon 14 to compare the proportion of the parent isotope, the carbon 14, that remains in the object to the proportion of the carbon 14 that is in the atmosphere. Given that carbon 14 has a half-life of several thousand years, we can date relatively old artifacts. Other very important uses of radioisotopes are in medicine. Radioactive tracers radioactive tracer isotopes can be used to measure a variety of metabolic processes. And then scans like positron emission tomography can be used to follow the decay and to follow how the isotope is concentrated in the body. There's a variety of rather dramatic images here on the screen showing how radioisotopes are used to measure and scan different bodily processes and tumors. Radioisotopes can also be used to treat tumors. When these isotopes decay, when they decompose, the energy and the nuclear particles that they give off can be used to damage or destroy cancerous cells. Understand that they can also damage and destroy healthy tissue as well. So the use of radioisotopes in both scanning and in medical treatment is a very exacting science. Now on to the electrons, which is the only thing we really haven't discussed. The arrangement or the distribution of electrons is critical to the chemical behavior of any given element. In the most basic sense, the arrangement or the distribution of electrons are described by the shells they occupied. Quite simply, shells are regions of space occupied by the electrons as they move around the nucleus. This is a very simplistic view, but it works well for us. Now, the number of shells depends on the number of electrons that an atom has, and the number of electrons that an atom has depends on the atom's atomic number, the element's atomic number. Generally, though, on the periodic table, period 1 elements have 1 electron shell. Period 2 elements have 2 electron shells. Period 3 elements have 3 electron shells, and so on and so on. We know how many electrons, the maximum number of electrons each shell can hold. Shell 1 holds 2, a max of 2 electrons. Shell 2 holds a maximum of 8 electrons in addition to the 2 electrons in shell 1. Shell 3 holds another 18, can hold another 18. Shell 4 can hold another 32 electrons, and on and on and on. And this is how we can build up these larger elements. Now, all the shells, all the electron shells that an element possesses, that an atom possesses, are important, but it is the outermost electron shell of the atom that influences the chemical behavior of the atom. This outermost electron shell is called the valence shell, and in the figure on the right of the slide, it is highlighted in red. So for period 1 elements, the first shell is the valence shell. For period 2 elements, the second shell is the valence shell. Period 3 elements, the valence shell is the third shell, and so on and so forth. It is the number of electrons in the valence shell that determines most of the chemical behavior of the atom. It is critical to note that elements with full valence shells are, for the most part, chemically inert and unreactive. Those elements with full valence shells are located in group 18 or group 8A, the rightmost column of the periodic table. Those are the noble gases. They are, for the most part, chemically unreactive because their valence shell of electrons is full. All the other elements, those with incomplete valence shells, follow what is normally referred to as the octet rule. And chemically, they will steal, share, or give away valence electrons so that they can have a full valence shell and be chemically inert, like the noble gases. Now, talking about the shells is a rather simplistic view of how the electrons are arranged, and we really do need one additional detail, and that is that within these shells are electron orbitals. The electrons don't simply encircle the nucleus with their shell. They spend their time in orbitals. These are three-dimensional regions of space in which the electrons are most likely to be found. These regions of space, these shapes, range from very simple spheres to very complicated looking dumbbells and donuts and clover leaves. And these shapes are derived from very complex mathematics that is beyond the scope of this presentation. But the bottom line is that each orbital can hold a maximum of 2 electrons, and these orbital shapes in 3 dimensions ultimately influence the type of bonding that atoms can undergo, and ultimately the shapes of the molecules that are created when these atoms come together. The formation of compounds and molecules will be covered in the next module.